We started talking about the channelization mechanisms, and we said that this category of MAC access control techniques, they try to divide the channel in different domains, such that the division of this channel will be allocated to each node and will be dedicated for this node so that we have no collision in the network. The first technique in that category is what we call frequency division multiple access. For frequency division multiple access, we divide the channel in the frequency domain. So the channel will be divided in the frequency domain so that each node will have a range, a sub-channel within that frequency spectrum, which is dedicated to this node. We said that the nodes can extract this sub-channel or this frequency range through the use of filters. So nodes usually use bandpass filter. So this is the receiving node. The receiving node can use the bandpass filter to extract the frequency range from a particular node in this whole spectrum. Okay? So by doing that, we guarantee that there will be no collision. So we also talked about the fact that we have to use what we call a guard bands. So between the nodes, there has to be some guard bands between each two nodes to account for the non-ideal filtering that we usually use, because the filtering will never be idle, will never extract this frequency range in ideal way. So we should account for this by accommodating some guard band between the nodes. So in FDMA, the available bandwidth of the common channel is divided into bands. We call them bands or subchannels that are separated by guard bands. So that's the simple technique of FDMA. There is, I have to tell you this, that there is another technique in the physical layer which is called frequency division multiplexing. Okay, but this happens within one node in the physical layer. Here we're talking about a MAC access control technique in the MAC layer, okay, which is totally different from FDM. So FDM is used in the physical layer. So the second technique is what we call TDMA. Of course, I know that you have gone through these techniques before, but that's why I'm going a little bit straightforward here. So in TDMA, simply, we divide the channel into time slots. Instead of frequency ranges, we divide the channel into time slots. So the whole spectrum of the network will not be divided in the frequency range. So each node that sends, it uses the entire frequency range of the channel. Okay? But in a specific time slot. And in that case also we don't have any collision. And here we also may use what we call time gap, which corresponds to the guard band. So we also use time gap. And this time gap accounts for the fact that the nodes will have different propagation time, right? So depending on the location of the node in the network, the propagation time, the delay that any node will have to transmit the signal from one node to another will be different, right? But this time slot should be equal for all nodes. So to account for this, we use also a time gap between these time slots to account for the variable delay that each node encounters within the network. Okay? So which is the same idea, except that here we use the time domain instead of the frequency domain. So just to go back to our usual meeting example. So TDMA is simply that we don't have any coordinator, we don't have anything, but the meeting is divided into time slots, and the number of the time slots equal to the number of participants in the meeting. So regardless of whether you have anything to say or not, your time slot will be dedicated for you. So when your turn comes, if you don't have anything to say, this time slot will be wasted. Because I have to dedicate this time slot for you. And of course, this is because I want to guarantee that there will be no collision. So to divide the channel into time slots, the good thing about this is that there will be no collision. It's simple. It does not require any coordinator. It does not require any centralized node. But at the same time, these time slots can be wasted if the nodes do not have anything to send. Okay? Another problem here, which is very critical, is what we call synchronization. So we said that these time slots are divided equally between the nodes, right? So the problem here is that you always have like a beginning of each time slot here. Okay? So the beginning of each time slot will have to be synchronized. And the synchronization here has to happen for the entire network. And remember the fact that the nodes, they have separate clocks, right? They have separate clocks. So if there is any time drift, again, similar to what we have talked about in chapter 3 and chapter 4, synchronization is a big issue here. Because the beginning of each time slot has to be synchronized between all the nodes. And regarding the fact that these nodes use different clocks, there may be some clock drift that will cause one node to start a little bit before or a little bit after the time slot that it should use. In that case, there may be some overlap. So first of all, what we do to avoid this, we also use the time gaps. So the time gaps are actually used for this purpose, to avoid, if there is any lack of synchronization, that there will be some overlap between the time slots. But also, they use some other techniques for synchronization. This is a big topic actually in TDMA. They use sometimes like synchronization signals. Okay, so they use like a common node that sends preamble, they call it preamble or synchronization signal, to inform all the nodes that be aware that this is the beginning of the time slot. So it's like a pilot signal. Okay, so the nodes, if the nodes have any drift in the time, they adjust their time to match the beginning of the time slot. So this way they can be synchronized. So synchronization is a big issue for TDMA. The disadvantages of TDMA. So in that case, the bandwidth is just one channel. So the bandwidth is not divided similar to FDMA. The bandwidth is 1 unit, but the time is the factor for dividing between the nodes. Okay? And as we said, since we're talking about the time, the issue of synchronization always brought up. The third technique in that category is what we call CDMA, or code division multiple access. So this divides the channel neither in the time domain nor in the frequency domain, which is a little bit tricky to comprehend. But in order for you to really understand the concept of CDMA, again, we go back to our meeting example. So imagine if we have a meeting and two people are talking at the same time, you will not be able to receive anything from, you will mainly consider that it's noise. You will not be able to distinguish one from the other. However, imagine that each one of these two people are talking different language. One is talking Chinese, okay, and one is talking Arabic. Okay? And they are talking at the same time. And you are listening, but the listener does not understand Arabic. Will I be able to listen to the Chinese from this composition? With a very high probability, yes. This is the main concept of CDMA. Okay? So there is composition of signals, which is what we called before collision. However, before we transmit anything, before we speak, let's just use some code and code the data that we transmit. Code it with a language which has no similarity with any other language. That's why I selected Arabic and Chinese. Okay? So imagine if those two languages are totally separate. They are not similar in any way. So if the two languages are coming to you and you as a person do not understand all these languages except one, chances are you will be able to extract this speech from all the other languages. This is the main idea of CDMA. So in CDMA, the nodes, they transmit at the same time using the same frequency. Okay? So what we do is that each node here, before it sends, it uses what we call a code. Okay? So before it sends the data, it multiplies this data by the code. Sometimes they call it a code, sometimes they call it a chip, sometimes they call it a spreading factor. Because what happens is that before I send the data, this code actually spreads the signal. And we'll see that. So each node will divide the data by this code. In order for you to be able to extract, of course, the composite signal will be a D1 times C1 plus D2 times C2 plus D3 times C, and so on. Okay? So all these nodes will send at the same time using the same frequency. In order for you to be able to extract any of this data, remember that my objective is to get, for example, D1, or to get D2, or to get D3. I want to receive this data. This is my objective. But I want to receive this data from the composite signal. In order for you to be able to extract any of these Ds from the composite signal, these codes have to have some properties. These codes have to have some properties. We call we call these codes orthogonal codes. Orthogonal codes or uncorrelated codes, which means that these codes, if you multiply any of these two codes, the result will always be 0. The result will always be 0. And if you multiply a code by itself, the result will be maximum. Which means that a code is highly correlated with itself, and it's not correlated with any other code. So these are the two properties that has to exist in all these codes in order for me to be able to extract any of this data from the composite signal. And we'll see how this is done. Okay, so simply the composite signal will be the summation of all this data multiplied by the code. So basically the product of the data vector multiplied by the matrix of all the codes. Okay? So this is an example of a representation of these codes. So remember that the data is 1 bit. It gets multiplied by a vector. So each 1 bit will get multiplied by a vector like this. And if you try to multiply, you will see these codes are calculated in such a way that if you multiply any of these two codes, and you can try it, for example, these two codes, you multiply -1 by 1, you multiply 1 by 1, and then -1 by 1, and then 1 by 1. Yani you vector product. Okay? So -1 by 1 is -1, plus 1 by 1 is 1, plus -1 by 1 is -1, plus 1. So the answer is 0. It's always 0. And you can try the same for any two pair of codes. Any combination of all these codes, the answer will always be 0. And if you multiply any code by itself, because simply we're using 1 and -1, because if we use 0 as one of the members in the codes, then the result will not be maximum. Because 0 times 0 is 0. But here, we always use 1 and -1. Why we use 1 and -1? Because the multiplication of 1 by 1 is 1. The multiplication of -1 by -1 is also 1. Right? So when you multiply the code by itself, the result will always be 4. Right? The result of any multiplication of the code by itself will always be 4, which is the maximum. So the result of vector product between any two pair of codes is always 0, and the result of multiplying the code by itself is always 4. Okay, so these are the important properties for these codes to be able to work for CDMA. So let's see will allow the CDMA technique to work. So in terms of data representation, remember that in terms of data representation we have binary. Our data is represented using binary, right? CDMA uses data representation that the binary 0 will be represented as -1. Binary 1 will be represented as 1. And if you don't want to send neither 1 or 0, okay, then I will consider that you have 0 signal. So -1 is representing the 0 binary, 1 will represent 1, and 0 will represent silence, which means that you don't have anything to send. So how is this data representation is going to serve the purpose of CDMA? So if Node 1 wants to send 0. Node 2 wants to send also 0. Node 3 wants to remain silent. And node 4 wants to send 1. So in that case, using the data representation, 0 is minus 1. And then we use the code that we have from the previous slide. We use the code for it, which is 1111. So this is a code, and we have all these codes are calculated in such a way that fulfills the two properties. The two properties, which are the codes have to be uncorrelated with each other, and they should be highly correlated with itself. Okay? Or in other words, the vector product of any two codes will always be 0, and the vector product for any code with itself should be maximum. Okay? So simply, what we need to do is the 0 we represent it using minus 1, and then we multiply this minus 1 by the vector. We multiply minus 1 by all the members in the vector. So the result will be minus 1, minus 1, minus 1, minus 1. So this is D1 times C1. Simple. One member divided by a vector. We do the same for all the other nodes. So for node 2, again, wants to send 0, which is minus 1, multiplied by the code, and the code here. And we'll see in a minute how we can calculate these codes. It's very easy. Okay? So minus 1 times the code, this is the result. And node 0 is silent, which means that the result is all zeros. And node 4 wants to send 1. 1 gets, using data representation, is 1 times this code. So the result will be this. And then what we need to do is to get the summation of all of this. A summation of vectors is simply the summation of each member in the vector. As simple as that. Okay? So 1 plus 1 plus 0 plus minus 1 is 1. Right? Minus 1, minus 1, minus 1 plus 0 is minus 3, and so on. Anything difficult here? It's very easy. Okay? So this is the composite signal. This is how the composite signal looks like, which represents the composite of the composition of all these vector products between the data sent by each node and the codes. So of course this is not dividing in the time domain, this is not dividing in the frequency domain, this is like a composite signal that represents all the data together. Okay? So the question is now, how can I extract D1, for example, from this composite signal? Okay? Or maybe D2, or D3. D3, I cannot extract this because this is 0 already, or D4. So that's the question that we need to answer. So to represent that in a time graph like this, node 1 wants to send 0, which is minus 1, which is we multiplied by the vector, and the answer is, this is the carrier signal. Okay? So this is the result signal, which is represented in the time domain like all minus 1 like this. And we put it on top of each other to be able to make it simple for the summation. So this is exactly what we have done. It's represented using a time graph. Node 2 wants to send 0, which is minus 1 multiplied by the code, which is again minus 1, 1, minus 1, 1. And then the summation of all of this is 1 minus 3 minus 1 minus 1. Again, so this is the composite signal. in the next slide, what we need to do, imagine that we want to receive station 3 because it was silent. Silent معناها it may be listening to the data from others. Now, station 3 wants to receive the data from station 2. In order for station 3 to receive the data from station 2, it needs to have the code of station 2. So the code of station 2 was 1 minus 1, 1 minus 1. So what node 3 needs to do is simply to multiply the code of station 2 by the composite signal. So minus 1 times 1 is minus 1, 1 times minus 3 is minus 3, and then minus 1 times minus 1 is 1, and then 1 times minus 1 is minus 1. So this is the inner product which is received by node 3. Okay? Remember that station 2 has sent what? 0 or 1? 0. Station 2 has originally sent binary 0, which is minus 1, which is represented by minus 1. So simply node 3, what it will do is that it will multiply the code for station 2 by the composite signal. It will get this result. And what it will do is that it will use what we call an integrator or accumulator. The accumulator, what it does is that it comes here and it says, okay, I have minus 1, so I go down minus 1. And then I have 1, then I go up by 1, which makes it a 0. And then I go down minus 3, and then I go down minus 1 again, which is minus 4. Okay? And then we use minus 4, we divide by the length of the number of the nodes, which is 4, which means that we get the average of this signal. Yani. This step is yani, in either way. If it's less than 0, then it's minus 1, which is 0. If it's more than 0, then it's 1, basically. Okay. So the original data that was sent is actually minus 1, which is 0. We can do the same thing for using the code from station 1 or using the code for station 4, and you will find out that it's fulfilled and you always receive the data correctly. So this is simply because again, we'll see the linear algebra of multiplying the codes by the data. It's very easy. So before this step, how do we calculate the codes for all the stations? So we use what we call Walsh table. Walsh is the name of the inventor who actually came up with the mechanism to calculate these codes such that the properties that we want are fulfilled in the code representation. So he said that first you can calculate Walsh table of length 1. So let's say that we have, for example, like 4 stations. 4 stations, you need to calculate W4. W4 is a matrix of length 4 by 4. Okay? So this matrix is always squared matrix. This matrix is always squared matrix. And the way you calculate W4 is from W2. And the way you calculate W2 is from W1. And the method or the mechanism is very easy. So W1 is 1. Then any other W will be, you get the same W and then you put it in the three members like this, and then this one will be the complement. Or it's yani complement, which means that it's multiplied by -1. As simple as that. So this is the rule. This is the mechanism. If you do that, then the multiplication of any two rows in this table will always be 0, and the multiplication of the row by itself will be maximum.
So W4 is 4 times W2, the same matrices, but 4 times.
Right. So W2 is simply constructed by W1, we get +1, +1, +1, +1, and then we multiply this by -1, which is -1. So this is W2. Okay? From W2 we can get W4. Again, we get the whole matrix. We put it like this 3 times, and then this one will be the complement or multiplied by -1. So these 1 and 1 and 1 will be -1, -1, -1, and this -1 has become 1. So if you do it this way, and you try the multiplication of any two rows, you will always find out that any two rows, this and this, this and this, this and this, or any combination of the two rows, you will find that the result will always be 0. Now we don't have to go through the proof of this, why this is happening and stuff again. We're taking things almost for granted because again the proof will require some sophisticated linear algebra derivation and stuff. Okay, but you can try it yourself and you'll find that it's very straightforward. Okay, so again, as you can notice, the W is always power of 2, right? So I cannot construct, for example, W3, right? It's always power of 2. That's why the number of the N, or the number of stations, has to be in a power of 2. Has to be 2 to the power of something. Okay? So even if the number of stations is less than, let's say the number of stations that you have in the network is 3, you have to construct W4 and then use the first 3 rows for codes, and the fourth one you can use it for extension. If there is a node that joins the network, then you use the fourth row. But here, using this simple mechanism, the N, or the number of stations, has to be a power of 2 in order for us to use the rules for Walsh table construction. Any question? So the number of sequences in the Walsh table has to be a power of 2. Has to be power of 2. That's easy. So find the chips. Again, we said that chips is spreading factor. All of them are terminology for the same thing. For 2 stations or for 4 stations. Well, for 2 stations we need W2. For 4 stations we need W4. We're lucky that he did not ask us for W3, because again we have to use W4. So we can use the rows on W3 and W4, which is in the previous slide. For if we have 2 stations, you can use the simple Walsh 2 table, and each row in the table will be 1 code. Remember that the Walsh 2 table is a is 1, 1, 1, minus 1. So this will be C1, and this will be C2. Okay? Similarly, if you have W4, the first row will be C1, second row will be C2, third row will be C3, and so on. Okay? So for 4 stations, we have the 4 codes which is in the previous slide constructed or extracted from the 4x4 matrix. Okay? So that's simple. So what is the number of sequences if we have 90 stations in our network? So again, if we have 90 stations, we said that the number of stations in the Walsh table, in the number of rows in the Walsh table has to be power of 2. So what is M in that case? M is 7 because we cannot have 90, so we have to have the number which is power of 2 which is above 90. So either 2 to the power 6 will give us a 64. We cannot use that. 2 to the power 7 will give us 128, which is more than 90. So that will work. So in that case, M will be 7 to have 128 rows in the Walsh table. So you can use the first 90 for the stations that you have, and the remaining ones will not be used, or can be used if there is any extension to the network. That's simple. Any confusion or any? Okay, straightforward. So we can prove the using simple linear algebra. We can prove that we can extract. What we need to do is to extract one of the D's from the composite signal. So the composite signal is simply D1 multiplied by C1 plus D2 multiplied by C2, and so on. So what we need to do now is to simply prove that using the symbolic linear algebra without having to go through numbers and stuff. Okay. If we multiply this composite signal by any of the codes, we will always get the data that corresponds to this code. Okay? And the proof is extremely simple. If you multiply this composite signal by, let's say, C1, okay? So if a station wants to get D1, this means that we need to multiply D by C1, which is D1 times C1 plus D2 times C2 plus D3 times C3 plus D4 times C4 multiplied by C1. So this will be D1 times N, because C1 times C1 is N, plus D2 times 0 plus D3 times 0 plus D4 times 0, which is D1 times N. Any question? Okay. So simply if we divide by N, we get D1. And again, this is because of the properties that we talked about, that any multiplication of any two codes will be 0, except if you multiply the code by itself, you get N. So if we divide this by N, that's it. We get the D. Okay. So this is the derivation. So if you multiply this by C1, similarly, if you multiply by C2, you get D2. Multiplied by C3, you get D3, and so on. Okay, so that's simply the proof. So when we divide the result by N, we get the data that we want. Of course, in reality, it's not as easy as that. I have to tell you that in reality, it's very complicated. What we are going through here is the ideal case. We did not account for noise, right? Because this -1 will not be received as -1 on the receiver side, right? And the composite signal will not be as ideal as we have shown here. And even if we forget about the noise, remember that when we send a signal -1 or 1 or something like that, remember that my distance is different from your distance, right? So there will be some attenuation. There will be some noise and stuff. Okay? So there is some complications related to CDMA because this corresponds, if we talk about the meeting example, of course we talked about two different languages, Arabic and Chinese, and we said that they are dissimilar in many ways. However, if one of them is talking from a distance and the other one is talking right next to you, and you want to get the one which is far, it's hard, right? Because by the time it reaches you, it's attenuated. So the distance, the noise, all of this affects CDMA more than any other type of mechanism that we talked about. Because if we're talking about frequency or time, whether they are far, they are close, the channel is divided in a discretized way. So using filters and stuff, you will receive a little bit attenuated signal, but it's totally separate. For the case of CDMA, using the codes, it works. And that's why CDMA is used for as a medium access control mechanism, as a physical layer modulation technique as well. It's used in many systems. All the 3G systems, by the way, are based on CDMA. All the 3G are based on CDMA. The G2 or second generation of cellular networks is based on FDMA and TDMA. But 3G is always based, or most of them are based on CDMA. This has lived for quite some time, despite all the challenges related to the near-far effect that I talked about now. The near-far effect, because if you have a composite signal you want to extract, you know that you have a composite signal with unequal weights. Someone is far, someone is close. So the summation is not as ideal as we can think, right? But they have some techniques to mitigate this situation and to be able to extract the signals with high probability of success. They have some solutions for this, okay? But the fact that you have a network and you don't have to have complicated filters to divide. And here, remember that even if you are silent, you can use more codes in the network, and you can actually, like for example, here we use a code of length 4. So we can think of this as that we have divided the bandwidth of the signal. This is basically equivalent to the fact that you have divided the bandwidth over 4. Right? So it's equivalent. Because we multiply each data by a vector of size 4. So we spread one bit by 4. So it's as if we have divided the bandwidth by 4. So what is the main advantage here? The main advantage is that you can actually, if your bandwidth cannot carry more than 4 subchannels, here you can use 8 codes, or you can use 16. And you can still get high probability of transmission. which means that you can actually squeeze more data using your bandwidth in a very efficient way, using CDMA. So through the composite signal, you can actually superimpose the transmission from all different nodes. And you can have very high, they call it very high spectral efficiency. Using the same bandwidth, you can transmit with higher throughput compared to FDMA and TDMA. FDMA and TDMA was really, the performance for it was not that impressive because of the fact that if the node does not have anything to send, the bandwidth or the time will be wasted, right? And they have techniques to try to reduce that inefficiency, but still CDMA has proven to be much outperforming and much better compared to these techniques. And it lived for مثلا 1 decade or 2 decades until they came up with what we call a OFDMA. So that's a recent technology that all the 4G standards, they use OFDMA. Okay. So that's so this is the end of this chapter.